Hello there. In this video we're going to talk about what people call or refer to as multifactorials. And you may see it represented as so in this diagram, where it has a bunch of exclamation marks. A bunch of exclamation marks does not mean factorial of a factorial of a factorial and so on. And it doesn't mean that somebody is screaming a particular number out loud in this case. But actually, pretty much what this diagram says is, this entire expression with all these factorial symbols is actually just equal to 5. So, what exactly does this mean, and how do we, calculate such a thing? So that's pretty much what we're going to be focusing on in this video. So let us first review off what a factorial is and how to calculate it. So factorial is usually just represented by one exclamation mark, and this is defined to be equal to the product of n and all its preceding natural numbers. So n times n minus 1 times n minus 2 all the way down to 1. Right, so this is the product of all preceding natural numbers from n down to 1. Alright, so with that being said, let's talk about what a double factorial is. So double factorial. Some people call it a double factorial, and some other people call it a semi-factorial. So both of these terms will refer to the same exact thing. So the double factorial, which is n with two factorial symbols. So this is going to be the product of n and all its numbers less than it, but in steps of 2. So instead of n times n minus 1, this is going to be n times n minus 2. And then we're going to multiply n minus 2 times the next 2 steps down, which is going to be n minus 4, all the way down to some number where this number is bigger than 1. So if we end at 1, then a is going to be equal to 1. But if we take, 2 steps forward and we get 0, that means we should have stopped at 2 in that case. So let's do a couple examples to sort of see how this goes out. So example. So suppose we want to know what 5 double factorial is equal to. So this is going to be the product of 5 and all its numbers less than it in steps of 2. So 2 numbers down from 5 is going to be 3, and 2 numbers down from 3 is going to be 1. So 5 double factorial is going to be 5 times 3 times 1, which is going to be equal to 15. Another example, 10 double factorial is going to be the product of 10 and all its numbers less than it in steps of 2. So 2 steps down from 10 is going to be 8, then 6, then 4, then 2. But if we go 2 steps down from 2, the next number is going to be 0, and 0 times anything is 0. So we're going to stop at this number because this number is the next one that is greater than or equal to 1. So if you multiply all this out, you should get 3840. And just another example, just make sure we got it. So 9 double factorial is going to be the product of 9 and all its preceding numbers less than 9, but in steps of 2. So 9 times 7 times 5 times 3 times 1. And once you all do that, you should get 945. Now, just like the factorial, you can break this down into some other pieces. For example, this is 9 times 7 times all the numbers less than or equal to 5, but in steps of 2. So 5 times 3 times 1 is the same as 5. Double factorial. So 9 times 7 is 63. We already found 5 double factorial to be 15. And again, you can see that that's going to be equal to 945. All right. So let's do another example and see if we can get a property here. So let's look at 10 double factorial, or let's just look at 10 factorial. So 10 factorial, as we know, is going to be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So what I'm going to do is I'm going to rearrange this product in terms of evens and odds. So I'm going to look at 10, 8, 6, 4, and 2. So this is going to be 10 times 8 times 6 times 4 times 2. And then I'm going to group our odd numbers together. So 9, 7, 5, 3, and 1. So this is going to be 9 times 7 times 5 times 3 times 1. All right, so this is the same as writing 10 double factorial multiplied by 9 double factorial. So 10 factorial is the same as this expression. So you can generalize the identity, or you can prove this using mathematical induction. But n factorial is always going to be equal to n double factorial times n minus 1 double factorial. So this is an identity that comes from factorials and double factorials. All right, makes sense? All right, let's go towards triple factorials and see how those will work out. So triple factorials. So triple factorials we are going to denote in a similar way. So n with 3 exclamation marks is going to be the product of n and all numbers less than or equal to n in steps of 3. So 3 steps down from n is going to be m minus 3. Another steps down is going to be n minus 6, and then m minus 9, all the way down to a, where a is bigger than or equal to 1. So as a guide and example, suppose we have 10 triple factorial. So 10 triple factorial is going to be equal to 10 times 3 steps down from 10 is going to be 7. 3 steps down from 7 is going to be 4, and 3 steps down from 4 is going to be 1. So 10 times 7 is going to be 70. 70 times 4 is going to be 280. So 10 triple factorial is going to be equal to 280. All right, that's cool. So let's see if we can get a similar property like we did for the double and single factorials. So let's look at 10 factorial again. So again, this is going to be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So I'm going to look at the 10 triple factorial terms, so 10, 7, 4, and 1. So 10, 7, 4, and 1, I'm going to group together. And then I'm going to look at 9, 6, and 3. So the steps between 9, 6, and 3 are all levels of 3, hence why we're looking at triple factorials. So this is going to be 9 times 6 times 3. And then I'm going to look at another couple terms. I'm going to look at 8, 5, and 2. So 8, 5, and 2. Notice the steps between 8, 5, and 2 are also equal to 3. So what exactly do we have in front of us here? So this is going to be equal to 10 triple factorial, and then 9 triple factorial, since we're moving in steps of 3, and then 8 triple factorial, and this is equal to 10 single factorial, right? So that means we can generalize the following identity. So we can say n factorial is going to be equal to n triple factorial times m minus 1 triple factorial times m minus 2 triple factorial. And that's the identity that relates triple and single factorials. So you may want to take a guess on how I'm going to approach the quadruple factorials. So that's going to be equal to n 1, 2, 3, 4. So n quadruple factorial times m minus 1, 1, 2, 3, 4. Quadruple factorials times m minus 2, 1, 2, 3, 4. And then n minus 3, 1, 2, 3, 4. Quadruple factorials. Right? So you can get that identity as well. So you may already realize that, drawing all these little exclamation marks may begin to be a little bit tedious, especially if you have a lot of them. So of course, some people denote the notation in a little bit different manner. So n single factorial is equivalent to writing n factorial subscript 1. So the subscript in parentheses is going to correspond to which factorial we're looking at. So n double factorial can be equivalently written as n factorial with a subscript 2. And if we have n triple factorial, this is the same as n factorial subscript 3. And similarly, if we have n 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, this is the same as n factorial subscript 7. So that's the 7th factorial, or the heptafactorial, or whatever you want to call it, and so on. So this is the so n factorial k. This is the kth multifactorial. This is the general case. All right, that's pretty much, what a multifactorial is. Of course, it ties into some combinatorial types of examples if you want to use it for that. Or as we see above, you can express like the product of even numbers less than or equal to something, or the product of odd numbers using double factorials, or the product of multiples of 3 or multiples of 7 or multiples of 8. You can use all these products of different types of numbers using multifactorials. And that's pretty much the gist of it, and some basic identities that are associated to the normal factorial and multifactorials as well.